Hi, so finally we're going to move on to something a little bit different, the second derivative test. So the first derivative tells us whether the original graph is increasing or decreasing. What the second derivative can tell us is telling us what kind of shape is that function making as it increases or as it decreases, because there's different ways that it can be doing that as it approaches either a maximum or a minimum. So there's the idea of a concave up or a concave down. So if the concave up on an interval, if on an interval I, if the derivative is increasing. So we're checking to see if the derivative is increasing. That tells us if we are concave up or concave down. I also have this so there's also a point of inflection where we switch from being concave up to concave down. That's what we're going to be looking at when we're trying to figure out when the second derivative is equal to 0. I have this cool graph that to kind of like demonstrate what's going on. So you can see in these two that they're both getting bigger. As we move across both of these, we are moving up. However, the shape of how they're moving up is different. This would be a concave down shape. Same thing with this one. It's also a concave down shape, but this is decreasing. This is a concave up shape, but it is increasing, and this is concave up, but while it is decreasing. Um, the second derivative test is not quite what you think. It's just not telling if it's whether it's increasing or decreasing. It actually follows a little bit of an opposite thing. If the derivative is 0 and the second derivative is negative, then we're able to get a local maximum. So we don't have to do that plus positive or negative check in order to figure out whether it's going to be a maximum or minimum. We can just check the sign of the second derivative if we know the first derivative is 0. Then there's going to be a local maximum. Now, it does work opposite. So if it's less, then it's max. And if it's greater, then it's a min. So watch out for that it's a little bit opposite for that second derivative test. Let's put these into applications a little bit. So we're going to use the concavity test to determine the intervals in which the graph is concave up or concave down. So to do that, we first need to figure out, well, what's our second derivative going to be? So I have to do the derivative on this thing twice. So I'm a little nervous that my thing's going to crash, so I'm going to do that, and then very carefully. Okay, cool. So y prime equals negative 4x cubed plus 12x squared minus 4. But we don't want to play with the first derivative. We want to play with the second derivative in order to determine the concavity of our graph. So we need to find y double prime. So that's negative 12x squared plus 24x is the second derivative of our function. Now I want to figure out where that is going to equal 0. Those are going to be the points of inflection. They're not going to be critical numbers. We got points of inflection now. So I'm going to factor out let's do negative 12x. So we get x minus 2 right there. So we get our points of inflection, our x values where we'll find points of inflection at 0 and x equals 2 for those two. So after we've got that, then let's put it into a sine chart and see what's going on with the second derivative. So if we put some number, so I got 0 and 2 on there already. If I put some number over here, so let's do like negative 10, we would get, if I put negative 10 right there, we get a positive value. And if I put negative 10 right there, I get a negative value. So overall, y double prime is negative right there. If I do something between 0 and 2, so let's do 1. 1 times negative 12, that's going to be negative. And 1 minus 2, that's also negative. So overall, we have a positive value there. And then if I do something bigger than 2, 10, so that is going to be a negative value. It's going to be negative 120. Hi, Mel. And then 10 minus 2 is also going to be positive. So, well, not also, I don't know. So that's going to be negative. So based on this, since we're negative, the areas where we're negative, we are going to be concave down. So you'll often see that abbreviated as CCD for concave down. And if we're negative over here as well, that's another spot where we're going to be concave down. So I'm going to put CCD once Mel's head's out of the way. And then where we're positive, that's where we're going to be concave up. So CCU is a nice abbreviation for concave up. You can see that down below that, though, I still wrote that real nice in nice big sentences. So y is concave up on the interval from 0 to 2. And we are concave down on the interval negative infinity to 0 and 2 to 0. Did you knock my pen on the floor? Okay, let's do another one. We want to find the points of inflection on this function. So the first thing we need to do is we need to figure out our second derivative of this thing. So we got to, do the first derivative. Our derivative of arctangent, I can kind of reference my answer key, but you hopefully have this one better memorized than me. It is 1 over 1 plus u prime squared. U squared. No, it's u prime over 1 plus u squared. So that's going to be y prime is 1 over, because the derivative of x is just 1 plus u squared, and that's just an x. So x squared. So now I got to find the derivative of that thing. Oh boy, y double prime. So really, that's just got like a negative 1 exponent, because we can say that this is the same as 1 plus x squared to the negative 1. That'll be easier to derive rather than trying to do the quotient rule on that thing. So y double prime is going to be negative, and then that denominator is going to get squared, so 1 plus x squared squared, increasing that negative 1 to a negative 2. And then I need to do the derivative of the inside, which is going to be 2x, and I might as well just slap that right on top. So we get negative 2x, 1 plus x squared squared. Now I need to figure out where that thing is going to equal 0. Yep. So there's an easy one right here, like that can equal 0, and then our whole thing will be equaling 0. If I check my denominator and I try to get a 0 out of that, we get 1 plus x squared equaling 0. We get x equals plus or minus I. So there's no real numbers that will create a undefined second derivative. So we don't have to worry about that. We have one potential point of inflection. I like to confirm that it is a point of inflection and not like a false one. So we can do a sine chart to just triple check that. It's a point of inflection, don't worry. But we can see that it's a point of inflection because y double prime should change sign as we go from one side to the other. If I put something that's smaller than 0 in there, so like negative 10, we get a negative of a negative number. And the denominator, we get a positive number squared. Negative 10 becomes positive when we square it. Add 1, still positive. Square that, still positive. So overall, we have a negative over a positive, which is negative, times another negative. We are positive in there for our second derivative. If we do our a number bigger than 0, so positive 10, we get a positive in the numerator. The denominator is also positive. So overall, we're negative here. Meaning y original function, not y prime, just y, is concave up right here and concave down right there. So we do have a point of inflection. Since it is asking for a point, I want to figure out where that coordinate point is. So it's at 0, and I just need to plug in a 0 right here the tangent of what is going to be 0. So I want sine over cosine, so I want 0 over 1. So where y is 0 and cosine is 1 is at 0. So 0, 0 is our point of inflection. And remember, arctan is not periodic, so it's not like we're going to get an infinite number of these. We're just going to get one, since we're not periodic for arc thingies. Use the derivative of the function y equals f of x to find the points at which f has a local maximum. So that's going to involve the first derivative. Local minimum is also going to be first derivative. Our point of inflection is going to be our second derivative. And I left the answers there just so we can, like, I know where I'm supposed to go, but how did I get there? This problem was kind enough to already give me the first derivative, so I can just figure out, okay, well, when's that sucker going to equal 0? Well, x equaling 1 and x equaling 2. So let's plug that into a sine chart, see what's going on. 1 and 2. If I put something like 0 in there, it's going to be negative. If I put like a half in there, that is going to be negative, positive, and a negative, so that's also negative. And then bigger than 2, so 10. So that's positive and a positive, so we got a positive. So we are decreasing and decreasing. So this is a false thing. So there isn't going to be a max or a minimum there. That's where the function was coming down, flattened for a minute, and then continued going down. It's not a max nor a minimum. But we do have, by the first derivative test, since we're going from decreasing to increasing, we have an absolute minimum, a local, and it's going to be the absolute minimum at x equaling 2. Now, to find the point of inflection, I need to figure out the second derivative. So y double prime, got to find the derivative of this thing. So that's going to be 2, derivative of the first. I got to do chain rule, but the derivative of the inside is 1. Derivative of the first times the second, plus the derivative of the second, which is 1, times the first, which is x minus 1 squared. Okay, I gotta clean this up a little bit. I am noticing that we have this double x minus 1 thingy. So rather than foiling all that stuff together and then trying to factor that, I'm just gonna factor that out right away. So we have an x minus 1. And then we have our 2 x minus 2's plus another x minus 1. So now I just have to FOIL all that stuff together and I'll get a much easier answer. If you FOILed first, that's fine, no worries. So that's 2x plus another x, that's 3x. And then we have negative 4 minus 1, that's going to be negative 5. So we do get 2 points of inflection at x equaling positive 1 and x equaling 5/3. You can check that same thing with a sine chart, but I know the video is going a little long, so I'm just going to kind of skip that part where, yeah, we're all good. Got those nice point of inflections. Determine the open intervals on which the graph is concave upward or concave downward. So doing that concave upward and concave downward test again. So first thing I need to figure out what my second derivative of this function is going to be. So, oh boy, I'm going to have to do quotient rule like the wind. So f prime of x equals, and I'm going to zoom in a little bit just so I have a little more space and it's a little easier to write. There we go. So I need to do the derivative of the top, so that's 4x times the derivative of the bottom, 3x squared plus 1, minus the derivative of the bottom, which is 6x, just 6x, times the top, which is 2x squared, all over 3x plus 1, oop, missed a squared, squared. Okay, let's clean up that numerator a little bit. So f prime, oh, don't do that to me, of x equals, we'll get 4x cubed, no, 12x cubed, excuse me. That screen freak out threw me off. 12x squared, x cubed, plus 4x, minus another 12x cubed. Oh, how nice. 3x squared plus 1 squared. So that 12x cubed minus another 12x cubed, that's just 0. So we're just left with a 4x in the numerator. Nice. That'll make my second derivative a little bit easier. I was worried I'd have a difference up there. That would have been a pain. Okay, so now I've got to find the second derivative, which is going to require another quotient rule. So I get f double prime of x equals derivative of the top, which is 4, times the bottom, 3x squared plus 1 squared, minus the derivative of the bottom. Okay, so that is going to be 2 times 3x squared plus 1. Derivative of the bottom is that. I got to do chain rule, so I got to do the inside, so that's going to be another 6x. Yep. Times the top, which is 4x. And then this is going to be all over that 3x squared plus 1. I got to do that squared again, so that's going to be 4. Oof, now that's going to take some simplification. Now, one thing I am seeing is each one of those terms, the two terms in the numerator and the one in the denominator, all have that 3x plus 1, which makes sense. Let's cancel it from each one. So I can cancel this one entirely. I can cancel one of the two that are right here, and then this 4 can become just a cubic. That'll just make my life a little bit easier. I'm running out of space, so I'm just going to move up a little bit. So I'm just going to shoot up here. So if I distribute that 4 in there, I get 12x squared plus 1 plus 4, not 1. And then we've got the negative 2 times 6, which is negative 12, times 4, which is negative 48. X squared all over, I think it's just that 3x squared plus 1 cubed. Okay. A little more simplification of that numerator. We get f double prime of x equals negative 36x squared plus 4 all over 3x squared plus 1 cubed. Okay, so now we can start thinking about, okay, well, what's going to make these things negative? Well, I'm sorry, not negative. What's going to make these things 0? So if I think about the denominator, what could I put in there that is going to make that thing equal to 0? Well, really nothing, because I'm squaring something and I'm adding 1 to it. So that's going to be producing imaginaries in order to get that denominator to be 0. So there's nothing there. That numerator, though, I bet we could do something with that. We could say, hey, let's grab that numerator, set it equal to 0. Get negative 36 x squared plus 4. I'm going to divide them both by 4 just to kind of make this a little bit easier. Negative 9x squared plus 1. So add the 1, divide by 9, so we get 0 equals plus or minus 1/3. Neat. Sine chart. So negative 1/3 and positive 1/3. Can I get my sine chart so I can see that and that thing? No. Okay. So I'm going to start with the easy one. I'm going to do 0. So if I put 0 into here, the numerator is going to be positive 4, so that's positive. In the denominator, I'll get 1 cubed, so that's a positive over a positive. So we are positive right here, so we are concave up. All right. And then if I do something like negative 10 in here, that will become positive, and then multiplied by the negative 36. Okay, that's negative 36. Well, some big negative number plus 4. That thing's basically negative up top. In the denominator, it would be become a positive, multiplied by 3, even bigger positive, add 1 better positive. All of that thing is just positive. So we are overall negative there, so we are concave down on that interval, which is what the answer was telling me. And then we should find the same result on the other side. This will get us a negative, and we're concave down from negative infinity to 1/3 and 1/3 to infinity. Huzzah! All right, once again, points of inflection, discuss the concavity. So this one's saying that we are concave downward all the time when we check the answer. So let's figure out why is this thing always concave downward. That seems weird. So we need to find our second derivative. So we got f of x. So f prime of x is going to be negative 1 minus 12x cubed. But that's not going to tell me anything about concavity or points of inflection. So I need to find f double prime of x. So that's going to be negative 36x squared. So the only point of inflection that we should be getting from that is where x equals 0. However, if we go into our sine chart, if we check f double prime of x, and we check its sign, if we put in like negative 10, we square that and it becomes positive, and then this thing is negative when we multiply it by negative 36. If we do something like positive 10, we get positive 100 times negative 36. It's still negative. So f of x is concave downward here, CCD, concave down, and it's also concave down over here. So it's just always concave down, and we don't actually have a point of inflection at 0. Now the reason for this, like if it was a critical number, we'd be like, yeah, that's still a critical number. We don't have to go through this positive or negative thing. A definition of a critical point is that if it's a critical point, then the second derivative is 0 or undefined. Critical number, however, goes in reverse. If the first derivative is 0 or undefined, you got a critical number there. So there's a reverse of that if-then statement. So with critical points, it is only, if you're a critical point, then we know, with points of inflection, if it's a point of inflection, we know the second derivative is 0 undefined. With a critical number, we say, okay, first derivative is 0 undefined, then that's a critical number. So x equaling 0 is not a point of inflection because it doesn't change. All right. Find all relative extrema. We're going to use the second derivative test to help us out. So the second derivative test lets us kind of bypass some of the work that we were doing with the first derivative test. But first, we got to figure out all that junk. So let's figure out, okay, well, f prime of x equals negative 3x squared plus 14x minus 15. So, and then let's grab the second derivative. F double prime of x is going to be negative 6x plus 14. We care about where the first derivative is going to be 0, because that's going to get us our critical numbers. So f prime of x, if we factor that thing, I'm going to pull out a negative to make my factoring easier. 3x squared minus 14x plus 15. Factor this, we get negative, it should be 3 and 5, I think, for 15. So, well, this is going to be 3 and 1, not 3 and 3. X. So I want to try to get 15 and, or 5 and 9, 5 and 9. So 5 and 9, so that'll be 15. Okay. And then let's see. 3 terms and a plus in the back sign doubles up like a Wendy's double stack. Huzzah. So f prime of x equals 0 when x equals 3 and when x equals 5/3. If we check what the second derivative is at those points, we can determine if we have a maximum or a minimum at those points. So let's plug those into our second derivative. So f double prime of 3 gets us negative 6 times 3 plus 14, which equals negative 18 plus 14, which is negative 4. Since that's less than 0, we have a max. Remember, it's a little backwards. That's less than 0. That is a maximum. So we have a local max at 3. And if we plug that back into the original, you get 9. Let's check that with 5/3. F double prime of 5/3 equals negative 6 5/3 plus 14. That is negative 10 plus 4, so that is 4, which is greater than 0, meaning we'll have a local min. At x equaling 5/3, and so that's 5/3. And again, you can just plug that back into the original function. It gets real gross. It's negative 275/27. Yuck. Yuck, yuck. But not worth our video time to look into. And that's it for the second derivative. And the second derivative test. So remember that where the second derivative is positive, we're going to say that's concave up, similar to how when we said the first derivative was positive, that was increasing. If the second derivative of the original function is negative, it is concave down, similar to how we said if the first derivative was negative, the original function is decreasing. Point of inflections are where we're changing from one thing to another. Okay. All right. I think that's it. Yeah. Bye-bye.